Today's episode dives into a topic that seems simple at first, how we choose sperm for IVF and ICSI, but turns out to be at the center of major technological innovation.
Absolutely. Sperm selection seems like a small step, but in reality, it's one of the most impactful decisions of the entire ART cycle. And with new technologies like microfluidics and artificial intelligence entering the lab, we're seeing a real paradigm shift.
Let's start with the basics. In natural conception, sperm undergo an extraordinary filtering process. They navigate cervical mucus, the uterotubal junction, and the oviduct, so only the healthiest, most competent sperm ever reach the egg.
Right. And when we perform ICSI, we bypass that natural selection entirely. Instead of millions of sperm competing, one embryologist picks a single sperm under the microscope. That's a huge responsibility and surprisingly subjective.
And the traditional lab methods, swim up and density gradients, mainly select based on motility. But sperm can swim perfectly well and still carry DNA fragmentation or double-strand breaks that compromise embryo development.
Exactly. That's why male DNA integrity has become such a central focus in ART. It's not just about motility anymore. It's about choosing sperm with intact chromatin to support early embryo development.
So let's move into the first major innovation, microfluidics. These devices mimic the natural environment by allowing sperm to migrate through microchannels without centrifugation.
And that's key. No centrifugation, because centrifugation increases oxidative stress, which increases DNA fragmentation. Microfluidics offer a more physiological, gentler way to select the top-performing sperm.
What really stands out is the evidence. Studies consistently show microfluidics reduce sperm DNA fragmentation by about 10% with improvements in progressive motility and morphology.
But the most fascinating part is how this translates to embryo development. Several sibling oocyte studies, including the one on the swim count harvester device, show higher usable blastocyst rates, better morphology, and even faster morphokinetics.
Yes, and that's important because morphokinetics, like time to blastulation, are strong indicators of embryo developmental potential.
We should highlight where microfluidics shine the most: high DNA fragmentation or high double-strand break populations.
Exactly. One study in the knowledge base looked specifically at couples where the male partner had elevated DSBs. With microfluidics, biochemical pregnancy, clinical pregnancy, and live birth rates all increased by roughly 30 to 35%.
That's remarkable. It means microfluidics aren't just improving lab metrics, they're influencing real clinical outcomes for some of the most challenging cases.
There's a critical lesson here, though. Microfluidics require careful workflow calibration. The Zymot validation study is the perfect example.
Right. When a clinic switched directly from density gradients to Zymot for IVF without modifying their protocol, fertilization rates dropped, even leading to total fertilization failures.
The fix turned out to be simple: a 5-minute centrifugation and medium change step. That adjustment restored fertilization rates.
It's a great reminder that new technologies must be integrated thoughtfully with a pilot phase and close KPI monitoring.
Let's shift gears to the second innovation, AI-assisted sperm selection, especially systems like SID.
SID analyzes sperm in real time using metrics like straight line velocity, linearity, and head movement pattern. It provides objective scoring, reducing the subjectivity of manual selection.
And the evidence shows its real strength is standardization. In sibling oocyte studies, outcomes were equivalent to manual selection, but junior embryologists achieved results closer to senior operators when using AI.
Exactly. AI doesn't necessarily pick better sperm than an experienced embryologist, but it makes the process more consistent across the team.
Which is essential for maintaining high-quality KPIs in busy, high-turnover labs.
So, how do you choose the right technology? It depends on the patient profile.
For high DFI or DSB cases, microfluidics is the clear winner. Several studies show improved blastocyst quality and higher live birth rates.
For labs struggling with operator variability, AI is the better solution. It standardizes ICSI sperm selection.
For severely low motility, microfluidics won't work. You need DGC, IMSI, or even testicular extraction.
And for cases with good sperm parameters but poor embryo development, microfluidics may reveal hidden DNA integrity problems.
Looking forward, what do you think is coming next?
Definitely hybrid platforms combining microfluidics with AI, physiological selection plus automated decision support.
And probably molecular profiling of single sperm, proteomics, epigenetics, helping us identify the most developmentally competent gametes.
As labs adopt more automation, the variability of human judgment may become a thing of the past.
So to wrap up, sperm selection is no longer just about motility. It's about DNA integrity, physiology, automation, and reproducibility.
Microfluidics and AI offer powerful new tools, but they must be implemented thoughtfully with proper validation and patient-specific use.
Thanks for listening. If you enjoyed this episode, stay tuned for more deep dives into reproductive technology.
And remember, smarter sperm selection means smarter, more successful ART. See you next time.